Hi everyone, my name is Peter Felf and I'm from the University of Sydney, and today I would like to show you how to work the volumetric system of Blender together with Matlab, so that you can do your own isosurfaces, you can do your own volume visualizations. So what you see here is actually all of that together. Sorry, I have the isosurface is not displayed very prominently. So you can see you've got an isosurface here. I've just rendered it with a lot of transparency, grain boundary model, and the volume data associated with it. And yeah, I'll just want to show you how to do that, give you the programs, and you guys can do it by yourself then. We'll make for very nice animations. I've linked some on my YouTube channel for you to watch, and also for very nice publication quality images. So the holdup with the whole tutorial now was actually giving out reference data. So what I've decided to do is actually write code that produces the reference data for you. So let's just clear all the variables I had produced before, and we'll start from scratch and we'll synthesize the reference data. So I'll just type that command in. It's actually a script, not a function. So all you need to do is type in synthesize reference data, which is a program that came with it, and it will produce a whole heap of variables, but it will also produce a .pos file, which contains a synthesized precipitate with 20 nanometers diameter, and that has an excess on the outside. And we're going to be analyzing that. And in order to do that, we can actually get rid of all the variables. So if you want to have a look into the script, after it's run, you will find all of the reference distributions and everything here in the variables. So there's nothing hidden from you. It will also produce reference data for a grain boundary and for a face boundary. This is stuff for another tutorial, which I've deactivated for now, but it does it very nicely as well. So let's load in the .pos file using the read post command. So it's sitting right there. And we need the solute, which I've given a fake master charge value of 2. So if we look into the .pos file or variable now, you can see there's a lot of 1s and there's the occasional 2. In the fourth column, which would, if this would be real data, it would be values like 27 point something, 40 point something, whatever your master charge is. Anyway, we don't need that for now. And we also need the bulk. So the bulk has a fake master charge of 1, as you've just seen in the variable. Alright, once we've created that, we actually do the voxelisation, which I've written the point to voxel script for, function for. And it's a relatively simple function that all you have to type in is actually, of course, what data you want. So it's called, the output will be called voxel. It will also produce a grid vector. What the grid vector is just 3 vectors, one in the x, one in the y, and one in the z direction. That shows you where the voxel centers are. We need that later for reference geometry. And when you do the voxelisation, you always start with the parent pos file. The reason for that is that that if you start with a sub pos file, there's always the possibility that it is a little bit smaller than your parent pos file. And what then could happen is that the voxel boundaries, the outermost voxels, don't cover your dataset later, other aspects of your datasets anymore, and this would lead to artifacts, of course. So that's why I always start with the parent pos file. This is about 6.5 million points, so it doesn't take very long at all. Then we want to voxelize the solute. And when we voxelize the solute, we use the grid vector that was produced before as an input. And never mind whatever it says here, that actually has no influence whatsoever. It should probably say 1. Oh, I forgot to say the inputs are the pos variable and the voxel size. So it's a 1 nanometer voxel size in this case. An atom probe usually end up with your voxel size somewhere between 1 and maybe 3 nanometers. And so this is actually synthetic data with a little bit of higher density, so 1 nanometer is fine. And we do that for the voxelized, for the solid data as well. One thing I have to mention is that this does not contain any smoothing. Usually in atom probe we very often use things like a transfer function to smooth the data, which helps with visualization. I'm not that keen on doing that for analysis data. I've integrated actually a more modern smoothing algorithm that's used very often for CAT scanner data, that uses higher order functional approximations of the concentration field that you're producing. This is probably a little bit more modern than what we're using in atom probe currently. Anyway, whatever you can justify, you can use, of course. So let's look into the data now. So the first data that we produce is, of course, a grid vector. It's very simple. If you click into the individual variables there, you just see it starts from minus 20 nanometers and goes in 1 nanometer steps up to plus 22 nanometers, and similar for the other directions, of course. And then we have the voxelisations, which is the voxelisation of the parent data set here. And you can see this is just layer by layer. The value is how many atoms do I have in each count, in each voxel. And this is that as a matrix. Usually, if you look into the voxelization of a species, you can already see the structure that it forms. So you can see here that if we're going in, you see a lot of zeros, but then you also start seeing high values. And if I go to somewhere in the middle, you can see things like that there is a higher density region here. So there's obviously some structure in there. But of course, visualizing that as a printed out list of numbers is not particularly convenient way of doing that. Anyway, from that we actually want to produce a concentration, and this is very simple. So we've got a voxelization of the parent pos file, which is all of our atoms, and we've got a voxelization, a corresponding voxelization. That's very important. A corresponding voxelization of the solid. So of course the concentration means solid divided by all atoms. We can do different things as well. So recently we've done things like isostoichiometry surfaces. Isodensity surfaces are very common, of course, especially if you want to explore the densities in your data set and things like that. Anyway, whatever you can come up with, whatever draws your fancy, you can do. In order to get the concentration, all you need to do is to divide the solid voxel the solid voxelization by the overall voxelization. Remember, you need to use the point divide, otherwise it's actually a matrix decomposition, not a division. And this is our concentration. So what can I do with the concentration? There's two main things we can do. The first one is to produce an isoconcentration surface, and the second one is to produce volume data. So let's start with the isoconcentration surface, which we very often use to produce things like proximity histograms. And in a slightly more modern twist to isosurfaces, which I'm not going to introduce right now, you can also use it for concentration mapping and for interfacial access mapping. Anyway, we'll do a marching cubes isosurface for now. And Matlab has that built in already, so you don't need to have any external programs or anything like that. Matlab can do that straight away for you. And the step one for that is that we need to produce a mesh grid which matches, which just tells it for each voxel what the coordinates of the voxel are, which is built in as well. So the command for that is gx is mesh grid, and there an inconsistency in Matlab comes into play, which is that between the isosurface and the rest of the coordinate systems, x and y seem to be swapped. I have no idea why. Matlab has a couple of glitches like that. Plus, there's always the fact that different programs use different coordinate systems. So whenever you do work like that, you need to pay attention to your coordinate systems. If they change direction, say if x and y are flipped or y and z are flipped, if they inverted, they can be inverted as well. So these are things to keep in mind when you do that sort of work. So we'll run the mesh grid command, and now we've just got the mesh grid. We've got the grid vectors, and you can see they're just the x, y, and z positions, and they match with the they match with our voxelisations. So in order to produce the isosurface, we'll just type in the isosurface command. So fv is just going to be the variable that holds the isosurface. So and it needs to have the grid positions and the concentration field and your ISO value in absolute values. And since we haven't gone over to producing percent, it's absolute values. So 0.2 is 20%. What the optimal ISO value is, of course, you would need to explore producing iteratively by producing a proximity histogram and then adjusting that. But there's a few things that are a little bit not that straightforward on that either. Anyway, I'll do a 0.2 now because I've synthesized the data, so I know that's the interface concentration, interface reference concentration, and there we have it. So what an isosurface actually consists of is just a list of vertices, so which is the coordinates of the points of the isosurface, and faces, which is the indices of the triangle. So it just says make a triangle from vertex number 7 to number 6 to number 91. It's very simple, and we can plot that in Matlab using the patch command. I've just chucked a few other things in there. It's got a blue face color, otherwise it turns out black. It's intransparent. Maybe we don't want to make it intransparent. I'll give it a little bit of transparency. And I've activated rotation and made sure that the axes are all the same scale. And there we have our isosurface. Of course, the isosurface, the mesh density is coupled to the voxelisation density, so it's a relatively dense one. But if you want to have a coarser mesh, you can of course recalculate your voxelisation, have a different voxelisation. So, of course, we want to use that outside of Matlab and we want to export it. I've made that really easy for you. All you need to do with the new fetchobj script is use the selection tool in Matlab. Select the object you want to export. It needs to be a mesh object, of course. So click on that. You can see it's highlighted now. And then you go fetch to obj, and it knows to pull out that object. You can of course pass which object you want, but for now we take the selection, and then we'll save it, and we'll just call it test precipitate 20% isosurface. Save. It pops up here. And we'll just show you what that looks like inside. So if I show that in the Finder and open it in a text editor, so you can always open OBJs in a text editor, you can see it's just that list of vertices. And once you scroll past the vertices, you'll see it's a list of faces and the name of the mesh. And that's all we need to export that. And the next thing you want is we want to export the volume data, the concentration field for visualization as well. And that's really easy as well. So all you need to do is type in volume to raw of the concentration and using the grid vectors. So with the grid vectors, the only reason that you need to put them in, you don't need to put them in, but the reason why you should put them in is so that my program automatically detects what the bin bounds are, where they are, on what size your volume is. And that is important because you later need to, the format it exports into is .raw, which is just 8-bit integers. So there's no header or anything, so there's no information included about how large your volume is, what the step size is, how many voxels there are. And you might remember that when you first export it, but if you go back to your data a week later, I'm pretty sure you're not going to remember that. That's why I've just created the program so that it puts all of that into the file name for you. So we'll just go volume to raw, and we'll call it test precipitate. And press save. This is not actually going to be the final name, so you can see the final name is going to be test precipitate 44 times 43 times 43, which is the number of voxels, and underscore 43 nanometers, 42 nanometers, 42 nanometers, which is the bounding box of the volume, and 0 to 0.555. That is what values are actually in the concentration field. And that is important because it's integer numbers, so it just can do 0 to 127. And we want to use that. We want to use those numbers as good as we can. That's why it doesn't go from 0 to 1, but it goes from 0 to whatever your highest value is. But then in your dataset name, it tells you, okay, when you made that file, the highest value you had was 0.555. So that when you later create a color bar or whatever for your visualization, then you know that the deep red is not a concentration of 100%. Anyway, so we've got all of that here. Just one thing that I'd like to do is just plot a histogram of the concentration values with. It just shows me roughly which values occur how often. Sorry, I should have created a new figure, because now I just plotted over the old one. So I created a new figure. And I made another mistake. It did it now for each column, so you need to force it to do linear indexing, which you do by putting in this designator. Now you can see it's much faster, and you can see we've got two main concentration areas. So if I set get current axis y scale, so we'll just change the y scale to go from 0 to 0.3. Sorry, it's the y limits. The scale is where it's okay, what did I do wrong? Let's run the histogram command again. 0.5. No, it should have been fine. 0.3. Anyway, just do it the old-fashioned way. So you can see we've got one area which is the precipitate with high concentration, and then we've got the base concentration here. So a good cutoff for our isosurface would have been in the middle, 0.15, 0.2, somewhere between 0.1 and 0.2 anyway. So let's have fun with that in Blender now. So in order to do that, of course, I'm gonna open Blender, and I'm using 2.73, and I'm gonna pause the recording here because I don't have screencast keys on 2.73. Okay, I'm back, and I've got the screencast keys and everything, so you can exactly see what I'm doing. I hope that all of the features that I was using were already implemented in 2.71. We're approaching 2.76 now. So in the default scene, I'll just go and delete the default cube and everything, and I'll leave the camera in there, as we might need that later. And first thing, I'm going to import the isosurface. So file, import wavefront obj. There we go. And that would be somewhere in my Dropbox. Where we have example data from the tutorials, volumetrics, and now we've got the isosurface. And here we just want to have Y forward and Z up, and that's pretty much it. And import, and that's our isosurface. That's what a margin cube's isosurface looks like. That's what the mesh looks like. So I was just going from object mode where I manipulate objects to edit mode where I manipulate meshes. Anyway, and then we'll go on to the second layer, and that's where I will, so we'll move the camera. We'll just lock the camera to the view and just move it somewhere where, oops, if your object disappears in the camera, what you need to do is go into the camera setting and set the clipping distance to more than 100 units, or nanometers in our case. I'll just set it to 500. And there we've got our precipitate. If we later want to visualize everything and do renders. But for now, I'm going to go into layer number 2. And on layer number 2, I'm going to add an object that will hold our volume. And that's, of course, going to be a cube. It's a cube-shaped volume. So I'll add a cube. Oh, and the cube needs to be at the center because our data is all centered. So we go snap cursor to center. And then add the cube there. And this cube will hold our volume data. So very often, if you've got atom probe data, it will not be centered around 0, but start at 0. So then what you might need to do is go into edit mode, GZ-1. Then you will see that your the origin of your object is at Z equals 0. And probably also invert it so that plus 0 becomes minus 0. Anyway, we don't need that for this tutorial. It's just going to sit in the middle. And we're going to add the volume to it. So the first thing we need to do is to give it a material. So I'm actually going to go into rendered mode. So volumes you can only see in rendered mode. That's why I go into rendered mode, which just shows you a black cube, which is a cube with no material and no lighting. And I'll just go into the world settings and make the world settings white so that we can see exactly what's going on while we're working. And I apologize for it being a little bit slow, but doing the screencast at the same time as my computer trying to render all the time seems to be a little bit of an extra load for my computer that it has to cope with. Anyway, so we'll go into the materials panel for this cube and add a new material, and we'll call this material volume, because it's going to be a volume material. And we'll select volume here, and now you can see already it's a sort of an average density volume thing with no structure to it. So it already does the volumetric rendering, but there's nothing in the volume that's interesting. So what we're going to do is add a volume texture, and that's actually what holds all of our data, and that's the raw file we were producing earlier. When you add a texture, you just need to make sure it's on materials textures and not on surface textures or world textures. It does it by default anyway. So we'll just add the texture, and the texture will be voxel data. And the voxel data format that we have is 8-bit raw. And that 8-bit raw file we need to load in. So just go, and now the naming comes in. So now I can see it's 44 times 43 times 43 voxels, and it's 43 nanometers times 42 nanometers times 42 nanometers. So we accept that, and now it's loaded in. But it doesn't do anything properly yet because it thinks it's 1 by 1 by 1 by voxel. That's why it's just still one gray value. But we remember that it's 44 times 43 times 43. So we'll just put that in here. 44 times 43 times 43. And now we can see it appearing here. So now this is actually the the texture itself, but the texture doesn't do anything yet. So we haven't made it do anything yet. So for that, we switch to still frame, because it could be an animation, so you can actually have evolving concentrations over time if you were to do a simulation, of course not from atom probe data. And the next thing we need to say is what will it influence, and it will influence the density of the material, and it will influence the emission color. So those are the two things that are going to be influenced by the material, by the voxels. And also we will make it ramp the color, but I'll get into that a little bit later. Anyway, so here you can see with the density we've got no emission yet, so we want to have emission set to 1, scattering to 1. The reason why we weren't seeing much was because there was a lot of scattering going on, so we need to set the scatter density to around about 0, and now you can see the volume. So this is actually already a volume rendering. So now it's slowly building up, but we haven't made it pretty yet. So going back into the voxelisation, we'll just change the colors for that. So and also we need to map the right coordinates. So the coordinates, we need to use the object coordinates of our objects that we used as the reference, and that is the cube. We should probably change the name at some point, but that's because we need to get it to the right size. So sorry, I'll go now into wireframe mode, and if I go and activate the isosurface as well, which is on layer 1, you can see that the volume is much smaller than the isosurface. These two things don't fit together, which means we need to change the size of the cube, and it's 43 times 42 times 42 nanometers. So we'll just put that into here. So it's 43 times 42 times 42 nanometers, and now these two things fit together. And if we go back into, sorry, I'll make that into a wireframe mesh as well. So we'll just go and add a wireframe modifier. So this is now a very thin wireframe mesh. And if I go into rendered mode, you will now see that the isosurface and our volume match up perfectly, but it's just got a little bit of an odd color. And also we just see the surface, which is a little bit boring. So we'll make a cut through our volume. And in order to do that, we'll just go on layer number 2, where our cube is, and we'll add another cube. So that cube sits in the middle as well. And we just wanted to make it about half as thick. So we'll make it in the x direction, we'll make it a little bit larger, so we'll make it 50. In the z direction, of course, the same, it's a cube. And in the y direction, we'll make it a bit less, so about 30. And we'll position it in the y position so that it cuts right through the middle, so that this edge lines up with the middle of the precipitate. So it's 15 nanometers off. And the next thing we're going to do is we're going to use a Boolean modifier. And what that does is it cuts through the first cube while the textual coordinates stay the same, so you can see it cut through your data. So we'll go into a Boolean modifier, use intersect, and I should use better names, but probably I won't bother right now. And we don't want the other cube to be visible or renderable anymore. It just does a clipping, and that's also how I did the animations. You just animate the clipping cube, and then whatever the remainder of your cube is, that's what's going to be rendered. So if I go into rendered mode now, you can see we have cut through there. Doesn't look as spectacular right now because we haven't put any colors in yet. But yeah, you can get a sense that it's very, very flexible when it comes to visualization. Anyway, so the reason why it renders so slowly is partially because of the render resolution step size. So I've told it to render every 0.2 nanometers, or that's the default, which is, while you're working with it, maybe a little bit too much. So I'll just go to 1, and you'll see it renders much faster now. Or I could even go to 2. Then of course this is larger than our voxel size, so we'll get a few artifacts. But in order to set something up, these sorts of resolutions are okay. So I'll probably just set it back to 1, because otherwise you could see that we were getting some color artifacts. Anyway, back in our texture tab, we will now change the coloring. So for now it's ramping up to this intensity, to this color, which is a bit weird, but that's the way it goes. But if we go into color ramp and switch the color ramp on here, we can actually influence that. So we can influence how the color ramping is done. And you can see here now this is actually a cut through our concentration field. Looks pretty cool. If I zoom out a little bit, you'll be able to see the outline of the entire data cube. I think it's pretty straightforward what it does. Maybe I'll leave it so that you can always see the edges of the cube as well. And then you can give it some color using the coloring here. So I also go into orthographic viewing mode, just a little bit more sciencey than using perspective mode, and add some colors here. Usually we start with blue and high transparency, go to green medium transparency, and go to red fully opaque. But of course, how to do the color ramping is completely up to you. Clamp means it clamps the color values for the RGB intensities, which, since our file goes from 0 to 128, is not actually important. So I'll just add another color marker in the middle, and we'll go to the first color marker with the index 0, and we'll change it to blue, but still fully transparent. Then we'll go to the one with the index, the one in the middle. I'll just make everything black first, then green. And it already had a medium transparency value, so it had a transparency value of 0.5. Can tweak that, of course. And then we'll go to the last color marker, and that one's fully opaque. And we'll make that one red. And that gives us already a pretty good coloring. It's not as nice in the middle, just because when you remember the I've closed it, unfortunately. If you remember the voxel values, some of the voxel values are actually way above of what we will actually get. So what we can do to fix that is just to crank up the relative intensity. So that's just a multiplier see it as a multiplier for the concentration values. So maybe 1.2 would be a good one. No, that's a bit too much. 1.1. See, we're still getting some color artifacts. It's simply because of the step size. I'll crank the step size up in a little bit, so just that you can see. But yeah, that's already some nice rendering. And we would want to change the... Oh, sorry, that's the wrong one. We would change the interpolation as well. So right now what it does is a linear interpolation between the voxel values. A better estimate is, not cubic B-spline, but cubic cat-rom, which is actually a function estimator. And there we have our data rendered that way. The colors are still a little bit off. You can fiddle here with the emission, so probably need to be a little bit. We need to have a little bit more emission to make it a little bit brighter, a little bit more glowy, and then move down the step size to something smaller, actually smaller than the voxel values. But then the emission was a little bit too much, so let's make it 1.5. Anyway, you get the idea. You can tweak the intensity of the colors and all of that pretty easily. So the emission value is just saying that each voxel emits light of a certain color, and the scattering value is just any light that passes through gets scattered with a certain with this color as well. which together gives you the coloring effect that we're observing. Yeah, that's it. We can add the first layer with the mesh, which is fully integrated in terms of rendering, and when you move around, you can see that the voxels actually go together. No, sorry, we've got an artifact here. So what I've done, unfortunately, is clicked map to bounds, which means it maps the entire voxel, all of the voxel values, to within the cube. But we were actually cutting through the cube, so we don't want that. So we'll switch that off. And now we've got the correct shading. This also explains why, when I was playing around with the coloring earlier, we didn't quite see the excess that's happening at the boundaries. So that's actually now what it should look like, and I think that's a pretty attractive render. So you can do that, of course, with or without the mesh. And yeah, that's all the trickery when it comes to the to volume displays. You can, of course, use all of the other visualization techniques. So you can use our atom plant plugin to throw your atoms in and render them together with the volume. You can throw your concentration maps in, throw your interfacial axis maps in, whatever you wanna display, and yeah, and get some really nice renders. Okay, that's it for today, and I hope that was a very, very helpful tutorial, and I hope to see some nice volume renderings from you out there pretty soon.